Okay, so let's take a look at this question, which asks us to use mathematical induction. We're asked to use mathematical induction to prove that for all positive integers n greater than or equal to 1, that this expression is true. Okay, so let's do that. We want to prove that 3 times 2 to the squared plus 3 squared times 2 cubed plus 3 cubed to the power of 4 plus dot 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 plus 3 to the power of n to the power of n plus 1 equals 12 over 5 6 to the n minus 1, where n is a positive integer. All right, so as usual with induction, first thing for n equals n plus k equals n equals 1, the left-hand side is just going to be 3 times 2 squared, which is just 12. Right. If we take a look at the left-hand side, when n is 1, this final term here is 3 to the power of 1 and 2 squared, which is already the first term. So that's really just one term, and that's the only one. None of these exist yet. And the right-hand side equals 12 over 5 times 6 to the power of 1 minus 1, which is 5. So it's 12. Therefore, true for n equals 1. Easy, simple step that you need to do. But now comes the part that needs a bit more work. So assume true for n equals k, where k is a positive integer. So that means 3 times 2 squared plus 3 squared times 2 cubed plus dot 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 plus 3 to the power of k 2 to the k plus 1 equals 12 over 5 6 to the power of k minus 1. And then we need to prove 3 times 2 squared plus 3 squared times 2 cubed plus dot 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 plus 3 to the power of k times 2 to the power of k plus 1 plus one more term, 3 to the power of k plus 1, 2 to the power of k plus 2 equals 12 over 5, 6 to the k plus 1 minus 1. Basically, this is for n equals k plus 1. Okay. So remember, we're trying to prove this left-hand side here. So right left-hand side, which is just going to be this thing here, this entire thing. So it's the left-hand side. Now, with induction, there is something you always need to do without fail. And that is when you're trying to prove this next case, you must use the assumption you already made, which is here. So we have this string of k terms, 3 times 2 squared plus 3 squared times 2 to the power of 3 plus dot 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 plus 3 to the power of k to the k plus 1, which we'll notice is just the first k terms here. And so we now have an extra term we need to deal with. But because this matches this, and we have our relationship that we're using, that one has to be used, and we're trying to prove this, then basically, we now just replace this with our assumption. And from there, it should hopefully be clear algebra work. All right, so we've got 6 to the k plus 1 minus 1, and we want to get it in this form. So the first thing that might be helpful is to just take out the 12 over 5. And so put everything in that bracket. Now that's 6 to the k minus 1 as expected. But this one, because we took out 12 over 5, that now means you're going to plus, I guess, 5 over 12 times 3 to the k plus 1, 2 to the k plus 2. Right? In the sense that when we expand this part out again, if you think of this as in brackets, 12 over 5 times this is itself, 12 over 5 times 5 over 12 cancels, and you're just left with 3 to the k plus 1, 2 to the k plus 2. Now remember, 12 is 4 times 3, which is 2 squared times 3. So that means I've got 12 over 5, 6 to the k minus 1, plus 5. Now, 2 squared cancels out with 2 here. So, I mean, I've got 5 times 3 times 3 to the k times 2 to the k times 2 squared over 12. Of course, the 3 and 2 squared cancels out with a 12. So that means I now have plus 5 times 6 to the k. Okay. So that means I'm going to have 12 over 5, 6 to the k plus 5 times 6 to the k, because I've got 2 to the k times 3 to the k is 6 to the k minus 1. Well, let's get ourselves a little bit of space, get rid of that. This is, well, 6 to the k, you've got 1 plus 5 of them. That's 12 over 5. That'll be 6 times 6 to the k minus 1. In other words, it's 12 over 5, 6 to the k plus 1 minus 1, which is the right-hand side. And so, therefore, we can conclude, if true for n equals k, it must also be true for n equals k plus 1. Of course, from here, that's the algebra work done. You just put it all together with the step 1 that we had earlier, because it's true for n equals 1, and because it must be true for the next one, 1 plus 1, so it must be true for 2. So it must, if it's true for 1, by step 2, it must be true for 2. And if it's true for 2, then by induction, it must be true for 3, 4, 5, and so on, for all positive integers n. And that's how you do that question.